Hello everyone to this section of the ORCA 6.1 release event, which will be about solvation effects, more specifically about solvation effects with DRACO and what's new within ORCA 6.1. For the people that don't know who I'm Lukas. I'm a PhD student with Stefan Grimme, and I mostly work on solvation topics, especially implicit models and the development thereof, and also statistical approaches. And if there are any questions with regard to what I'm saying in this talk or with regards to my work, just feel free to send me an email. I'm very happy to discuss. This talk will be structured into a few parts. I will quickly go into a motivation and recap, then go into what the DRACO scheme is, what it does, and what the idea behind it is. Then about the usage and setting of the new features. And then I'll show a few examples and applications that you can now do. DRACO stands for Dynamic Radial Adjustment for Continuous Solvation, and you can easily combine it with CPCM or SMD, and it was shown to generally improve solvation-free energies with, in principle, no additional computational cost, as the DRACO step before the calculation is practically for free in comparison to the DFT calculation afterwards. However, up to now, it wasn't possible to do optimizations in ORCA with using DRACO, and you will get this nice error message if you do. However, now we do have analytical gradients available in ORCA 6.1 that can be easily used with the DRACO scheme now. Next up, I would like to cover the idea behind DRACO and also the physical rationale behind it. In an explicit approach, we of course have explicit water, in our case water molecules present, that interact with our solute. And because of the need of conformation sampling that's always also present, but also due to the now huge size of our system, it is for most cases practically impossible or not feasible to do it. Because of this, typically one prefers implicit solvation models that are very efficient and easy to apply. And these models of course, need to consider how to separate solvent and solute, which is now our solvent continuum. And for this, one typically constructs a cavity which now separates or creates this boundary between solvent and solute. In the case of, for example, CPCM, this boundary is also used to solve the CPCM equations on, which then gives us back the polarization energy. Now, in the CPCM, what happens is the electrons or our solute polarizes the solvent continuum, and because of this, due to this polarization, there's a charge density created, a polarization charge density, which of course also again interacts with our solute. So and this cycle of polarization and back polarization and so on and so forth is called self-consistent reaction field. Now, these charge densities that are created are obviously interact via Coulomb law because it's just electrons, charges basically. That means that the distance or the size of the cavity is very, very crucial when it comes to polarization energies or energies in our case. And additionally, when we look into the explicit approach again, we can see I've drawn in these three blue arrows, which would indicate an average distance between the water molecules, in our case, and the solute. It is pretty clear that in the cases of the strong hydrogen bondings, so the two arrows on the left bottom, the mean distance during an MD, for example, will be much, much, much smaller compared to the ones to the one on top with the hydrogen that is attached to the carbon atom. And in principle, this has to be somehow included in this cavity construction because the cavity basically gives us some sort of hopefully meaningful distance between solvent and solute. And because of this, the question is really, how do we choose this appropriate radius? Now, there are many ways to construct the cavity. One would be, or one very famous one, because it makes physically a lot of sense, is, for example, the isodensity scheme, which places the boundaries or the cavity exactly at points where the electron density of our solute is the same. With this, one obtains a cavity that is very, very nice tailored to our solute. However, it is very hard to derive gradients for it, and also already to solve the SCF, because every SCF step, the density, the electron density changes, you need to construct the cavity again. And because of this, one typically uses just van der Waals spheres placed at the atom positions with a specific radius to construct this cavity, which is very, very easy to do. And for that, typically one uses just one fixed radius, which is very often the gas phase van der Waals radius times 20%, for example. So 20% larger than the gas phase radius. So overall, obtaining these radii is very, very difficult because they already include, of course, the solvent-solvent interaction that we are interested in the first place. One way to approach this is the DRACO scheme. The DRACO scheme is a highly empirical approach which aims to providing system and atom-specific radii to construct this van der Waals cavity with. Now, the DRACO scheme uses as descriptors, before solving the SCF, an atomic partial charge that is obtained via, for example, the classical EEQ model, so a classical charge model, and a coordination number. And those two are fed into a scaling function that I don't want to go into too much detail here, that basically just scales the gas phase van der Waals radii, or the CPCM radii, or SMD radii, by some factor up or down. And with this, you basically obtain then the DRACO radii that are then used for the cavity construction. I have with me here the example of the acetic acid anion in water. Now, this acetic acid anion in water you can see on the top left for CPCM with the CPCM radii, and on the bottom right the CPCM plus DRACO radii. And you can clearly see there's certainly a difference, especially the radii for the oxygens are in the DRACO approach smaller, about 80% of the ones with CPCM. And the hydrogens are also slightly larger compared to the ones in CPCM. Another example is this alanine glycine dipeptide, which is a Zwitter ion. And on the top left, you can see the cavity for the CPCM, and bottom right, the one for DRACO. However, additionally now to the cavity shape, I have plotted the surface charges that are obtained after convergence of the SCF, so the CPCM surface charges. And again, comparing those two cavities, you can see that there are certainly differences in how the cavity looks like, how it is constructed, and of course also due to the size of the radii and the cavity, the surface charges are also different. I already mentioned before that energies are in principle straightforward because we just compute the DRACO radii, construct our cavities with these modified radii, and solve our CPCM equations, and that's it. However, for the derivative, so the gradient of the CPCM with dynamic radii or non-static radii, it's much more complicated because now our radii are also a function of the nuclear coordinates. So on the left we have again, or the example of the acetic acid anion. On the left there's the relaxed structure. Now in CPCM, when we just displace, for example, one of the oxygens, of course we move the oxygen and also the cavity that is attached or constructed by the oxygen is also moved. However, now in the DRACO scheme, we not only displace our cavity, but also the radius changes, which means we have an additional change due to the DRACO scheme. Because of this, the gradient is more complicated, and if you're interested in the details, you're very welcome to look into the paper that we wrote on it. However, either way, we have now consistent analytical gradients in ORCA that yield a smooth potential energy surface and thus allow easy geometry optimizations using DRACO. Next up, I would like to go into a bit more detail on how to use the new optimization features combined with DRACO. So in principle, it is very straightforward. You just have to tell ORCA, well, you want SMD or CPCM with your solvent of interest. You tell ORCA you want to have the DRACO scheme, and additionally just tell ORCA, well, you want to optimize the structure now. For example, here shown as with the new native GFN2 XTB implementation. Now, DRACO is usable with CPCM and SMD, and solvents that are currently parameterized are water, acetonitrile, DMSO, and methanol. For optimizations currently, you can only use the EQ charge model. The reason for that is that the CEH charge model does not have analytical gradients yet, and also you cannot use the isodensity scheme together with DRACO. So the isodensity scheme to create the integration grid size or use an integration grid size that is depending on the radius. Because we found out that in some cases where the radii change is rather drastic, the energy or the potential energy surface is not continuous anymore, which can lead to issues in optimizations, which means now the number of grid points is fixed when using DRACO combined with an optimization. And if you're interested in, of course, speeding up the calculation because you have very large structures or just want a crude estimate, you of course can reduce the number of grid points, for example, to 110 or 50. However, of course, at an expense of accuracy. Next up, I would like to go into a bit more detail on examples and applications of the new DRACO gradients. Now, as a quick recap, I have with me the Solvation free energies on the Minnesota Solvation database. On the left, you can see the regular CPCM and SMD variants, and on the right, the DRACO CPCM and SMD variants, and all errors are shown in kcal per mole. And you can clearly see that comparing the left with the right window, that the energies decreased tremendously. And the reason for that is that especially the ions and zeta ions are improved a lot upon using the DRACO scheme. However, also the neutral species are slightly improved upon using the DRACO scheme. Now, to investigate geometries, we compiled a small test set containing heteroatom dense organic molecules, but also transition metal complexes and also a few highly charged solutes and also ions and salts. And generally we found that the CPCM and DRACO geometries agree rather well. So they are generally very, very, very similar. However, there are a few noticeable differences between CPCM plus DRACO. And these three geometries were the three results where the final CPCM and CPCM plus DRACO geometry differed the most. And for all cases, you can see that the DRACO modified CPCM yielded geometries that were much more folded openwards or slightly more exposed to the solvent compared to the CPCM variant. It's not very large, especially compared to the gas phase structures. So CPCM plus DRACO still are very, very similar. However, the trend still holds that the CPCM plus DRACO geometries are generally more so exposed to the solvent, so more folded openwards. Of course, one is not limited to small structures. As an example, I have with me a DNA molecule taken out of a benchmark set that has roughly 1,000 atoms. And I optimized this using the new native GFN2 XDB implementation and CPCM plus DRACO in water. And this is also possible to do in ORCA if one desires. However, it is worth mentioning that because we use CPCM and we need to invert the matrix, the expensive part here in the optimization and also during the STF is the CPCM part compared to the GFN2 XDB part here. Next up, I would like to quickly go into the timings required for optimizing geometries upon using DRACO. Now, as an example, we looked into a linear chain of alanine units that we basically extended 1 unit at a time up to 20 units, which is roughly 200 atoms. And you can see two curves. So the dashed one, so the bottom one here, is the time for just the CPCM part of the gradient. And the top two lines are timings for the overall gradient, so also including the gradient for example, the density functional. And comparing the ones of CPCM and CPCM plus DRACO for the purely CPCM part, there's clearly a difference, for example, especially when it comes to larger structures. And here for 200 atoms, it is roughly twice as expensive to calculate the CPCM gradient upon using DRACO. However, when we now look at the overall gradient, so the one when we have, for example, in this case, Arthuroscan 3C present, the fraction of the CPCM part, because it is rather small, does not really affect the overall computation time of the gradient. And also I have another relevant example with me, which is an optimization of the alanine chain with 10 alanine units in water using Arthuroscan 3C on 8 cores. And this optimization from this initial structure takes around 2 hours, 40 to 50 minutes, depending on if one uses CPCM and CPCM plus DRACO. And in principle, the CPCM plus DRACO optimization takes 7% longer and 3 cycles more. However, if you look into the optimizations shown on the top left, you can see that the CPCM plus DRACO final geometry is also further away from the one without using DRACO, which means that the 3 additional steps are just needed because the structures differ more. And because of this, this is the main reason why it takes longer. Now that the analytical gradient is available, one can also calculate the numerical Hessian. And here shown for thymine. So the red line is the experiment. The yellow line is the CPCM one, calculated analytically, which takes 1.5 minutes. And the CPCM plus DRACO Hessian is calculated numerically, which takes then 5 minutes. And you can see that, of course, due to the influence of DRACO in this case, the R spectrum also differs slightly, and actually in this case agrees better with experiment than the one with plain CPCM does. At the end, I would like to quickly give a short conclusion and outlook on what I talked about. So there are now analytical CPCM plus DRACO and SMD plus DRACO gradients available within ORCA 6.1, and of course one can thus also use numFrac now, so calculating the Hessian numerically and also, for example, transition states. We saw that DRACO improves the prediction of solvation free energies drastically, especially for ions and polar solutes. And it is very easily usable just via the simple keywords that are already known. Now, the question is, what's next now that the gradient is available? And well, maybe next time there's a major ORCA release, I'll be here again telling you about a new solvation model, but that will be left to see. At the end, I would like to thank you for your attention. If you have any questions, of course, feel free to reach out via mail or also via Blue Sky, for example. And yeah, thanks again for your attention.